So 3.2, more application of the derivative type of stuff. So this one is this one is about Rolle's theorem. Now I don't like Rolle's theorem specifically, but it does make sense. It's just a specific case of a bigger one because all it says is if you're looking at some graph and you choose 2 points, if the slope between those 2 points is 0, and it's continuous and it's differentiable and all that stuff, of course, and you choose 2 points and the slope between those 2 points is 0, that means that in at least one place, the slope of the tangent line is 0. And that just makes sense. That's something you can see right here. And the whole idea being that if it comes back to the same place, it's got to turn around. So that's the idea. If the slope of the secant line is 0, then somewhere the slope of the tangent line is 0. And notice how this is just a specific case of 0. It works the same no matter what it is. If you find the slope of the secant line, so like you could also say, instead of choosing those 2 points, choose these 2 points. If you find the slope of the secant line, you know that in between those 2 points, somewhere that has to also be that slope. And that just makes sense. I don't even think you need to prove that. I think that's kind of common sense. So let's just kind of do it. So find the two x-intercepts. Show that f prime of x equals 0 at some point between the two x-intercepts. Right, so here we're not trying to find it. We could, which is easy enough. That's why this seems kind of silly to do this stuff. But sometimes it's not so easy. So we can still verify that it is at some point. We don't even need to find it. So what are we going to do? We're going to find the two x-intercepts. How do you find an x-intercept? Set the y value equal to 0. Factor. Minus here. So now we have our two x-intercepts, 1 and 2. And so really all they're trying to say is like, let's picture that. We have 1, we have 2. If we draw the secant line between those 2 points, the slope of that line is 0. And since this is a polynomial, polynomials are always continuous, always differentiable. So since this function is continuous between 1 and 2, and it's differentiable between 1 and 2, and the slope between those 2 points is 0, that means at some point in the middle, the slope of the tangent line will have to be 0 between those two x-intercepts. And that, of course, just makes sense to us because we know this is a parabola, so we know that somewhere down here, the slope of the tangent line will be 0. All right, let's keep moving on. So let f of x equals x to the fourth minus 2x squared. Find all values of c such that f prime of that equals 0. So here we do want to find them. So that's fine. We want to know where f prime of c equals 0. So f prime, the derivative, equals 0. So we're just going to take the derivative, 4x cubed minus 4x, and we're just going to set that equal to 0. It's kind of hard to see. Let me change the color. So you got to factor. I'd factor out of 4x. You're left with x squared minus 1. You keep factoring. X plus 1, x minus 1. And those are all the places that the derivative will be 0, that the slope of the tangent line will be 0. And so we just need to check because we only want them between negative 2 and 2. But yeah, all of those numbers are in between negative 2 and 2. So at all those places, the slope of the tangent line will be 0. So see, here is the general form. So instead of just looking for the slope to be 0, we're just looking for the tangent line to be parallel to the secant line, for them to have the same slope. So look at what we're going to do here. We're going to find the slope of the secant line between 1 and 4. So that's why we're doing f of 4 minus f of 1 over 4 minus 1. So what is that? Well, 5 minus 4 over 4 is 1. 5 minus 4 over 1... Hang on. 5 minus 4 over 4 is 4. It's 5 minus 1. 5 minus 4 over 1 is 5 minus 4, which is 1. Over 4 minus 1. So the slope is 1. So we're looking for everywhere in between 1 and 4 where the slope is 1. And we know it's continuous. So we know that it's Yeah, we know it's continuous. It's only not continuous at x equals 0. So we just need to find a place on this function where the derivative is equal to 1. So we'll take the derivative. F prime of x is the derivative of 1 over x is negative 1 over x squared. So this is positive 4 over x squared. And we're trying to see where that's equal to 1. So cross multiply square root x equals positive or negative 2. And then look at where we care about. We only care about 1 through 4. So it is true that at negative 2, it'll have a slope of positive 1. But we only care about the 1 at 2. So the only one is at x equals 2. All right, let's see how this goes. So 2 stationary patrol cars equipped with radar are 5 miles apart on a highway, as shown on figure 3.14. Oh, should we get figure pi? As a truck passes the first patrol car, its speed is clocked at 55 miles per hour. 4 minutes later, when the truck passes the second car, its speed is clocked at 50 miles per hour. Prove that the truck must have exceeded the speed limit at some time during the 4 minutes. So the idea here is, how long did it actually take him to travel? Like, what was his average speed? Because that's what the secant line is, right? It's like the average speed. So if we look at this, that they went 5 miles. They went 5 miles. And how long did it take them? It took them 4 minutes. So it's 5 miles per 4 minutes. But in reality, we want hours. So there's 60 minutes per hour. So we do that. What's 60 divided by 4? 15. What's 5 times 15? 75. Oh, this dude's a wild one. So his average speed was 70 miles per hour. So that's the idea with that's one of the things the mean value theorem will tell us. His average speed going between these two cops was 75 miles per hour. So that means what happened was he went slow, and then somewhere in the middle he zoomed it up to like probably 80 or 90, and then they slammed on their brakes again once they hit 50. Because if the average was 75, based on what this tells us, that means at some point the speed must have been 75. How can we draw this out in a graph? It's like we're here. We'll say this is minutes. So at minute 0, he's like 0 miles from that first cop. And then at minute 4, he's 5 miles from that cop. And so, yeah, we know that this slope is 75. And so even though he's going slow here and then slow here, well, here, let me do that better. So he's going slow here, but then he's going to have to go fast, and then he's going to have to go slow again here. That's what it looks like. So we know that at least one point in there, he's got to hit 75. In reality, we probably know that he's got to hit at 2 points in there, because he's got to go faster than 75 at some point. So that's interesting. Oh, wow, and that's the last problem in here. So that's it for this calc. So remember, you can find these on YouTube. Probably already on YouTube if you're watching this. But yeah, make sure you try to keep up. And make sure you're practicing on your own too. Like, you should pull up the textbook, go to 3.2, practice some of those problems. But tomorrow we'll get into 3.3.